slept, and now I'm all rushed. So, including the coffee. So what we're going to do today is, first of all, finish what I wanted to show you last time, so all the intro stuff, and then we're going to delve into discrete time systems. The next couple of lectures are going to be a review of 120. Who didn't take 120? Difficult. It's a very short review of 120. I'm going to assume that you know all the material from 120. We're going to zoom over DTFT, Z-transforms, DFT, all this stuff very quickly. So if you haven't, then you have to catch up. Okay? Any questions? Who attended the lab session yesterday? Okay. All right, just a few announcements. Homework 1 will be due today. It's going to be out today. Not due today. Be out today. Homework 1 due to the TA will be due today. Lab 0 is out. It's going to be due next Thursday. We're going to send on Piazza exactly how to do the checkoffs. Webcast. This actually class is webcasted. So you can watch the lectures online. But let me warn you, all the cool stuff that we're going to do in class, you're not going to be able to see. So it's just like the boring material kind of thing. All the demos and like interesting things I'm going to show you, not going to be in the webcast. Yes, I want to introduce our TAs, our wonderful TAs, Frank Ong on the back, and John Tamir over here. Yeah, John is the head TA, and he's going to manage Frank. All right, let's move on. Last time I showed you, I wanted to give you some examples of applications of DSP. And one of them was computational optics. I showed you how some of our faculty made some money out of it and then got a faculty position. But the idea is that you modify how a system is acquired, then you add computation in order to get more out of it, something that you could not have done otherwise. Okay, so for example, being able to focus after the fact that you take a picture. Only using computation. Of course, you have to change the other side of the system, how the data is acquired, that actually has that information in it. And I'm going to actually stress out quite a bit. It's really important, even if you are doing signal processing, to know all sides of a system. If you know all sides and you can control how data is acquired, how it's generated, you can do with signal processing or with DSP much more. And we're going to talk more about this. Did I show you this example? Did I? I showed you CT. Okay, CT is amazing. And the fact that it completely changed diagnostic medicine, the fact that you can look inside somebody's body by making shadows from all directions and using ideas like filter back projection or signal processing in order to produce an image. I talked a little bit about MRI, the fact that MRI data is acquired in the frequency domain. And what is even a two-dimensional, what is this two-dimensional Fourier transform? What does it even mean? What is the Fourier transform in image? We're going to actually cover that in class. Okay? But making a scanner do all these noises, acquiring all this data, allows you to then produce these beautiful images of a brain. Let me just annoy you too. I'm just not the only one that's getting annoyed. Yeah. This is a beautiful sound, beautiful sound. You're going to enjoy it. Okay. So the other thing, as it turns out, using MRI, you can make the... Did we talk about that? No? Okay. So with MRI, you can get really, really interesting contrast. One of them is changes in be able to be sensitive to changes in blood oxygenation. So your brain, when it's active and when it's when neurons fire, they need more or less more oxygen. The brain actually controls the blood flow and the level of oxygen that goes into areas that are more active and brings them more blood. So you can actually correlate by measuring the changes in those blood oxygenation in MRI. You're able to correlate that with brain activity. And here's what happens when you produce a visual stimulus that is periodic to a person looking at that stimulus. And while acquiring images in MRI, you can see how certain voxels or certain pixels in that image would generate something that's also periodic. You can then do cross-correlation, correlate with it, and extract places where actually have brain activity. And the thing is, here at Berkeley, people have taken that even further, where they look at the whole visual system through, so looking the eyes, brain, MRI as a whole nonlinear system, and then showing persons movies and while measuring the fMRI signal and trying to characterize as a nonlinear system. And once they characterize this nonlinear system, they can show an arbitrary stimulus like this one over here and try to infer just from the fMRI data what this person is looking at. And I have to say, not too bad, okay? Which is quite amazing. So it's taking this significantly forward. One of the things that I actually work on is the idea is that, well, I showed you that images can be compressible, right? I show you the JPEG compression in a camera. Well, it turns out that MRI data or medical imaging data is also compressible. And if it's compressible, maybe we can reduce the amount of data that we acquire in the first place and not acquire everything and then throw it away. Why, just collect less data. And then using the fact that it's compressible and computational techniques in order to collect less data, use some prior information that's compressible, and then produce images as if we collected all the data. Okay, so this is all about what you can do once you have stuff on a computer and you compute this, use DSP techniques. Okay, so the one thing I wanted to show you, which we're going to use in class, is, this is the last example, is software-defined radios. What is a software-defined radios, really? What it does, if you look at a traditional radio, maybe 15, 20 years ago, what it would do is the hardware will receive the signal, will demodulate, it will filter it, it will then do something about, interpret the data, all in analog, and then play it as sound or as something else. Okay? So the output can be either analog or digital bits that comes out of it. But you'll have a lot of analog components there. So the demodulation part, the filtering part will often be all analog. What software-defined radio do is really just uses something very simple. Uses an RF front end, which takes the electromagnetic signals and converts them into samples. So it samples directly the electromagnetic signals. Okay, so you have just a simple hardware, or it's actually I wouldn't go as much as simple, but you have a hardware that basically will sense the electromagnetic signals through an antenna, and then will go and produce samples of that electromagnetic field. Then you convert those into samples, and then once you have those samples of the raw RF signal, then you can implement all the processing chain in software. Okay, so you have just one small device that converts these things into samples. Once there are samples, you can implement everything, like extremely sophisticated radios in software. So there's a lot of advantages to this. Of course, it's the flexibility, right? If you had a radio that was an FM radio, then it would only do FM. If you have an AM radio, it will only do AM. If you have a digital radio, it will only do that. Now you can have a single radio that just by changing the software, you can make it into anything. It is, of course, upgradable. You can do firmware upgrade. That's kind of what you do sometimes. Sometimes when on your phone, when you do an upgrade, you also upgrade the software that runs on the radio of the phone. And you can add really sophisticated processing. And of course, kind of like an ideal processing, like things don't change, right? Your filters don't change with temperature anymore, right? Because they're all just, just coefficients that are, matrix multiplication, basically. Okay? So this is, of course, already used in a lot of consumer electronics, like this, GPS, of course, Wi-Fi. They're all doing that thing. But a lot of it is kind of like hidden from you. You don't have access to this. But here's what a few years ago, there came this device, and I don't know if you can see it. This is this USB dongle here, right? This is a device that is meant to watch TV in a DVB-T format. Okay? DVB-T format is a format for digital television in Europe. So you really cannot watch anything in the U.S. using this. Okay? It's not support. Nobody transmits with that kind of format. So these companies, a company came and made this chip. Realtek made this chip that is able to capture, digitize those signals, and then decode the TV signals out, okay, and then display that on your computer. A chip that does the whole thing. Okay, so this kind of looks like this. It's really inexpensive. You can buy that for about $10 to $15. This thing, it's consumer, but it uses this RDL 2832 and the E4000 or 820T chipset. Okay, and as it turns out, they also wanted to implement FM radio on it, and I said, well, we can implement that in hardware, or how about we'll just use that in the driver. So we'll send samples to the computer, and the driver would then interpret and demodulate the FM, and then be able to play that. Okay, instead of just implementing it on the chip. Once they did that, there was a guy that wanted to make a driver for Linux, and he realized that samples are actually being sent. And once samples are being sent to the computer, well, then you don't have to use it to watch TV. You can use it for anything else because you have samples. And as it turns out, you can make this device into a really inexpensive software-defined radio, which you can use for something else, not just watching TV. Okay, and I'll show you some examples today. But here's what's extraordinary about this device. Okay, so you have RF in comes in, you have a tuner that demodulates a particular frequency down to close to DC, and then you have something that converts it into samples. And then samples are then sent using the USB out. So you've got a whole RF chain. It's very simple type of processing, but at the end you've got samples coming out. Okay? But you know what's amazing about this? Whomever in the EECS department, the entire EECS department appears on this device. Okay? So if you've taken EE117, that's all this port. So E&M. 140, 142, all the analog circuits, they're all in this device, which is the tuner. Of course, if you look at the transistors, and if you look at the crystal, 130, so the devices, if you want to understand how they work. 140, 141, analog and digital mixed signals, they're all kind of built here. ADCs, D2As, they're all in this device over here. And then there's a lot of 120. There's a lot of 120, 121, 122, 123, and 126 that are built over here, but also process the signal that comes out. Okay, that's the signals and systems part of the department. And then, of course, the application layer, all the software that is constructed afterwards that is actually able to implement all those are at the back end. So really, the entire department is just in this $15 device that can do amazing, amazing things. Now, what's cool about this is every one of you is going to get one of these devices. We're going to do labs with this. We'll provide you with a very simple interface to Python. And then you're going to get homeworks and labs based on this. And, of course, the final project could use this. But here's something very simple that you can do. Here's an example of the code. You just initialize this device. You set a sampling rate. You pick a center frequency, some gain. And then you start getting samples at a certain rate. Once you get those samples in Python, now it's just arrays. You take those arrays and you perform signal processing on them. And then you can, for example, listen to radio station. You can listen to police stations. You can listen to digital radio. You can do lots of stuff. And I'm going to show you a small demo using this device. This is actually using what's called okay, you don't want to see my calendar, I guess. Right. But there you go. So this is a piece of software called GQRX, which basically interfaces to this device, and then in real time kind of does all sorts of types of demodulations. Okay. So now, I'm speaking to this microphone, right? And this microphone is also connected to a transmitter, and that transmitter is connected to this recording system, and then also plays on the room, right? Well, that's great. But here's the thing. Let me take this TV device, extract samples out of it, and then tune to a particular frequency, so it's around 581 hertz. And you can actually see the FM signal now on the waterfall. This is called a spectrogram. This is the spectrum, and you see the FM signal being demodulated by this device that was really meant for watching TV. Unbelievable. Just by the fact that you have samples, now I can implement an FM radio that can replace the whole system here of receiving that probably you would have paid, I don't know, like $200 to do this. Now just with software and like a simple device, I can just do that. Okay? Which is quite amazing, right? But here's another thing. Anybody has car keys here? Anybody has a car? Yeah? Yeah? We've done that before? Okay, all right. So car keys. Okay? Car keys, turns out, cars transmit at around 315 hertz. And let me switch instead to demodulate amplitude modulation. Second. Okay, can you press down your key? Nothing? I'll use mine. Anybody else with keys? So this is really what my transmitter here transmits. And I can now use this device to pick up this and interpret what bits it's actually sending. Can you hack a car with that? Actually, yes. If I recorded this and you ran now to the car. Right, so my car is not new. But can you do something about it? And I would say, yes, on this device, because people didn't think about that. But how many devices out there expose certain amount of information that with this simple device you can actually pick it up? For example, listen to tires, right? Tire pressure in cars, they transmit they have transmitters that transmit the pressure, so the car receives it on the sensors. So it can, sometimes, if your tire explodes, the car actually compensates for this. You can actually pick those signals up. Okay? Fast track, you can pick those signals up. There's a lot of stuff you can do just with this device. Okay? So the ability of taking samples out of the spectrum, you can then do whatever you want with them and interpret it, which is amazing, I think. And so we're going to give you this, and you can play with this as much as you like. This is a great, great device and a great way to understand actually what's going on in the radio spectrum, which obviously a lot of you are not exposed to because we cannot hear or see the radio spectrum. But there's a lot of stuff going on there. Okay? All right. Any questions? No questions. It's all clear. Well, at least one. I want one question. One question. Yeah. Okay, so let's say you recorded now my signal. It's a rolling code, so it changes over time. But let's say you recorded now my code, and then you go and you run now to my car, and with a transmitter generate the same code before I go and press, then you'll be able to open my car once. Blocking is pretty easy.
And then save it and then use it.
Yeah, that's another way to.
Did that with Garage.
Yeah, you can do that with Garage Door as well. So there's a lot of stuff that is very interesting that you can do with those devices, and you're going to get. Yep.
So if you went out to your car and open your car door once, that means that you can then also no longer open your car?
No, I can open. I probably will have to press like a couple times. It's a rolling code, so it's. I think there's maybe like if I pressed on this like more than 1,000 times, probably I won't be able to open my car because it's going to look for like 1,000 codes around it. Yeah.
So does it mean if you keep opening long enough, you just keep opening the car door? Where's the radio?
Okay, let's move on. I know you're excited about opening my car, but I can just give you the key. You can just open it. Yeah. Okay. All right. So I think the reason that I also think that it's really good to know both sides of the system is because we're going to give you this device that okay. So we're going to use radios in this class, and we're going to give you this kind of a radio here, and you're going to connect something to its audio and then play with the computer and like send like digital information through the audio and then transmit it over the air and do digital communication with this and all sorts of stuff. But you're going to have something that would, it has a cable and connects to your computer and like you have like a sound card and then all this stuff here. But you're going to be transmitting, for example, like 5 watts next to your computer. I'm transmitting now. So, do you see what's happening? Yeah. So you got to be aware of the actual physics because like you're going to transmit, it's like I'm not getting anything. And the reason you're not getting anything because you just completely overloaded your analog to digital converter because it even turns on a light here, a light bulb, right? This is like wireless power transfer. Okay, I've got here an antenna and a light bulb in the middle. And this is what happens when things are picked up. Okay, so you have to understand kind of the connection with the physical world and the DSP, and you have to be able to debug a lot of stuff like that. And this is part of being an engineer. So it's not just the DSP part. It's really kind of the understanding the whole system. So I do recommend taking one of those classes just to understand. If you want to do DSP, taking those classes will also be helpful. Now, we're going to use amateur radio or radios as a tool for teaching you DSP. So everybody in this class will get an FCC license, a technician class at least. If you want to get a higher level, please go ahead. You're more than welcome. And we might reward you for that. Maybe you get to keep the radio. Each student will get one of these radios. Okay, this is it's a really nice FM radio. 5 watts. I've been able to communicate through satellites using this device. It has a pretty amazing range of tens to sometimes hundreds of miles, depending on line of sight and so on and so forth. We'll use this for digital signal processing, communication labs, and the project. Now, the reason I thought that would be great is you raised this March 12th. I think the exam is ignore this part. But the reason I actually like it is because it's a wonderful way of learning everything that has to do with this department, right? With the ECS department, all aspects of it are manifested in eventually making communications. And so I've personally got into this by teaching this class. And I learned so much. And if I figure out, if I learned something so much, probably you could also benefit from this as well. So this is what we're going to do. I'm going to post another, the actual exam is posted on the web. Fine. But again, there's this EE198-13. You can register in order to get credit for studying for the amateur radio class. You don't have to register for this one. I do recommend for you to attend if you're going to take the exam. It's going to save you some time. And it's also lots of fun. Okay? Questions? Yeah.
So we're going to take that course with you. Do we buy the book?
The what?
Do we have to buy that book or is that just for self-study?
you don't have to buy this, but you have to pass the exam. So the book is it's $12. It's $12, and it's really nicely written, and you learn a lot from this. Yeah. Really? Wow. That's great. Okay, so let's move on. Yes. Yeah, the book is the Oppenheim and Schaefer, 3rd edition. If you have 2nd edition, it's okay. Yep. And we'll give you extra material when we cover stuff that's not in the book. Okay, so let's move on. Let's talk about discrete time signals, and the rest of which, of course, is not a lot. The rest of the class, we'll talk about discrete time signals, discrete time systems, but we're going to develop again kind of a language. Maybe you've seen this at other places, a little bit different. So we're gonna talk and give you a short overview of things. So sometimes discrete signals will be samples of a continuous time signal. For example, like here you have a continuous time signal, and then you make samples of it. So these are sample at, for example, at intervals of t seconds. Okay, so these are one example, but it can also be inherently discrete, and we mentioned that last time. So here are some basic sequences that we're going to be using. One thing that you've probably seen before is the unit impulse, and the unit impulse is a discrete Dirac function or the discrete delta function, which is defined as being one at the origin of the or n equals 0 and 0 elsewhere. It is actually very different than the continuous time delta function or impulse function. It's a very different beast. This one is easy, is a trivial beast in the sense that it doesn't explode to infinity and all sorts of stuff like that. Okay, so things are going to be slightly different. It's kind of like same but different. There's a lot of stuff that you can relate to from the continuous time, but stuff are also different when you go to the discrete time. There's weird and small nuances that you have to be able to understand because they are going to impact your systems and your implementation and understanding of signals. A unit step is positive. It's 1 from n greater or equal to 0, okay? And 0 before that. Exponential, so capital A, which is the amplitude, times alpha to the power of n. These are exponentials. And so you can see that depending on what alpha is, you're going to get slightly different sequences. For example, when alpha is between 0 and 1, you get something is going to be decaying. Okay? When alpha is negative, you get something that's a little bit oscillatory, okay, but still decaying. But when alpha is actually greater than 1, you get something is going to explode. Okay? And that's going to have implication. If you have a system like this, it might be non-stable. Okay? Now, sinusoids, right? We all understand or kind of what sinusoids are, right? There's something that's oscillatory with some period, right? And that's great. But there's something slightly different when we talk about discrete time. For example, let's look at just a very simple concept of A times cosine omega 0 times n plus phi. What is this, by the way? Phase. Phase. This is this amazing concept, phase, that I hope you'll be able to get. People don't get phase. Don't get really what phase means. But phase has a lot of information in it. And hopefully you'll be able to see this. It doesn't have to be actually a cosine. It can also be a complex exponential. Okay, and who hasn't seen this before? Representation? Great. Okay, so the question is, is this periodic or not? And what is really the definition of periodic? The definition of periodic is if you add some n to like an offset to a function, it is the same as that function. So if you basically shift that function by one period, it's going to look the same. Okay, that's the definition of periodicity. period. Can you say that? Periodicity. Thank you. In discrete signal. And the question is this periodic or not? I mean, cosine, you know, in continuous time is periodic. Is this periodic right now? That's right. Okay, so it depends. Now things depend. It's not clear that it's actually periodic. As it turns out, it's going to be periodic only if omega naught over pi is rational. If it's not rational, it's never going to be periodic. Right? Crazy. It is crazy. And if you want to find a fundamental period, of course you need to find a small integer k of n such that omega 0 times n equal to pi k and so on and so forth. So it's going to have a certain period. But it's different. Okay? It's slightly different. We have to understand this. And so here's just an example of a period of 5 over 7 pi n. We'll have a period of n equal 14, where k equal 5, and when you have pi over 5, then this is 10, and so on and so forth. And if you add these two together, then you can find a period which is going to be n equals 7, and so on and so forth. Okay? Let's move on. Here's another difference. Which one of these is actually a higher frequency? In continuous time, we understand what's a higher frequency, right? If you have f or big omega, if it's larger, it's higher, right? Well, what about small omega or omega naught? Which one's higher? Appears to be that 3 over 2 is higher than 1, right? Right? Appears. Yet, it isn't. In fact, pi is actually the highest frequency you can achieve. There's nothing faster in the digital world or higher frequency or higher change you can achieve when you get to pi. The reason is, there you go for something positive, negative, every sample. So the period is 2 samples. Right? That's the shortest. You can. If it was 1 sample period, it really is not changing. So 2 sample period is the fastest you go. And that's you can achieve with pi. So if I increase it, I get a phenomena which we'll see as aliasing, where things start slowing down again. Crazy. Right? But that's the discrete world. Okay? Because cosine of 3 pi over 2n is also equal to cosine pi over 2n, which pi over 2 is really less than pi. Okay? These are the same. Okay? This is what aliasing is. And so the period here is 2 and the period here is 4. Now remember, from 120, when you looked at the DTFT is periodic. When you look at the frequency or the Fourier transform of discrete signals, they are periodic with frequency. And since they're periodic with frequency, there's the highest frequency, which is always going to be pi. Okay? Pi is the highest frequency. So as I increase stuff from omega 0, omega equal pi over 8, yeah, this looks like a sinusoid. This also looks like a sinusoid. And then I increase it over to pi. Now it doesn't even look like a sinusoid, right? It looks like, like a zipper. And then I can continue on and just go the other way. And as I increase it, my frequency is actually decreasing. Okay? So this phenomena, we'll see, it's called aliasing. It has a lot of implication when things we do with discrete signal. Okay? Questions? So let's talk about systems, right? We show, there's the signals that are discrete. By the way, we can have so when we do the analysis, sometimes we'll analyze things as discrete just in time. Okay, so just discrete values, but with continuous representation. So we'll analyze those. But we'll also analyze the case where we have discrete samples but also discrete representation. Okay? And there's going to be implications of that because there's going to be what's called quantization effect. Okay? But even without thinking about quantization, there's a lot of things that are slightly different. Same, but different. So if you think of a discrete system, what is a system? System, something comes in and something comes out. Okay? Out of that system. So we got this beautiful X coming into my system, and then Y coming out. What properties that system could have? One of them, let me give you a hint, causality. Throw one in for you. Okay? Causality. What does causality mean? Well, what it says is that the output only depends on past inputs. Okay? It cannot predict the future. Yes? It is. Oh, boy, you get $1 for that. By the way, you get $1 for every mistake you find. But I kind of debugged them so much, so like the first times that I was teaching this, like I lost a significant amount of cash. But now it's not actually too bad, so I can afford it now. I almost finished my startup funds on this. Yeah. Let's see. Notes. All right. Great. New note. Cash for EE123. Remind me your name. I forget. Angela. That's right. Angela. $1. Incentive to pay attention. Maybe I'll make it 2. I'll make it 2. I'll up the ante. $2. Okay, $2. What? $2. Okay, so Y depends only on previous samples of X. Give me more. Give me more properties that you know about systems. Yeah. What? Stability. That's right. Stability. That's a good one. Linearity. Who said linearity? Did you interfere?
One of us said linearity.
But I asked him. Time invariance. That's a good one. What else? Yeah. Memoryless. Right. Anyone else? Any more? Okay. All right. So memoryless. That's a good one. Y depend only on current X. There's no need for storage. Example. Y equals X squared, right? Like if you square something, you don't have to store anything. Okay? Linearity has 2 parts of it. One of it is a superposition. So if I take 2 signals and I impose them on top of each other, what I could have done is first run one through the system, run the other one through the system, look at the outputs, add those outputs. Those should be exactly the same as first adding and then pushing through the output. Okay? That's what it means. And that's a great property. If you have a linear system, that's an amazing property because it allows you to analyze things separately and not together. That's great. Homogeneity is if I scale something, I put something really strong in, the output's going to scale in the same way. Okay? So that's great. I'm scale invariant in that sense. Okay? Very important. Okay? And in many cases, even though we think that our system is linear, it might be linear across a certain range. And that often happens, especially, for example, in those software-defined radios. Yeah, it works, things are fine, are all linear. I transmit a sinusoid or some frequency, I pick it up, it's all great. I increase the amplitude, yeah, I see it increasing. At some point, I'm going to overdrive my receive chain, and things are going to be clipped and no longer linear. Okay, and you're going to see that, actually, when you deal with those. So it could be approximately linear for a certain range, but then it might not be linear anymore as we push it. And of course, there's not a lot of systems that are really, really linear when you increase things significantly, right? Like if you look, let's say, at some oscillatory effect. I mean, if I put like a nuclear bomb, close to, things are not going to be linear anymore, right? There's nothing going to come out. It's going to destroy the whole system, right? So yeah, right? Not going to be linear anymore. Okay, so time invariance, very important property. Very important property. What is time invariance? Time invariance is you don't care if the signal is shifted in time. Shifting in time, the input will shift exactly the same the output. Okay, that is important. Are we time invariance as people? Absolutely not. If you give information to a 4-year-old, not going to get it as well as you guys. Okay, so I can not shift what I'm like this class to like I not start teaching when before you're born. And still assume that it would be great, but it doesn't work. And then Bibo stability. Bibo stability means that if I have a bounded input, my output is guaranteed to be bounded. It's also a very important property, because what it tells me is that as long as I keep my signal from exploding, the input, my output is not going to be exploding too. All right. So let's look at some examples. When you think of causal, linear, time invariant, memoryless, bibostable system. So I'll give you one for free. X of n equals x of n minus nd. That's a time shift. Is this causal? Sometimes, depending if you shift it forward in time or backward in time. Okay? If you shift it backward in time, no, not causal. But forward in time, yeah, it is causal. What about linear? Yes, it would be linear. So time shift is linear. What about time invariance? Yes, it is time invariance. And by the way, time invariance can also be shift invariance. What is shift invariance? Well, if my signal is not time but space, then people call it shift invariance. What about memoryless? Do you need to store memory? Yes, unless you're doing nothing. If you don't do anything, then you don't. And what about stability? Yeah, it should be stable because we're not really amplifying anything, we're not changing anything, we're just delaying something. Okay, so it is stable. What about accumulator? Who says causal? Raise your hand if you think causal. Absolutely, it is causal. Accumulator is causal because you only rely on past samples. What about linear? Can you represent it by a matrix multiplication? An infinite matrix multiplication? Can you? I mean, do you see any nonlinear combination of those samples? That's not linear, right? It is a linear combination, hence linear. What about time invariance? Tricky, a little bit. What if it's kind of like an integral. Accumulator is kind of like an integral. What if I start integrating earlier? Do I get like early? Come on. Raise your hand if you think it's time invariant. Raise your hand if you didn't think it's not time invariant. You lose. It is time invariant because it doesn't matter where I am when I start integrating. My integrator is going to be delayed. Okay, so if I shift my signal forward, my output integrator is going to be delayed. What about memoryless? Raise your hand. Memoryless? Yes. Memoryless? No. Great. Yeah, of course you need memory because you need to keep those values. What about stability? Is it stable? What if I have a constant value and I just accumulate? What happens to it? It grows, right? It grows. So not bibostable. Okay, so what about compressor? Compressor is an interesting signal where you basically sample a discrete signal every m values. Okay, so it's kind of like a sampling operation of the discrete signal. Okay, we only keep every m value. It's good that you're sitting there and you're separated. Okay. So, causal? Causal? Really? I compress something. It's not causal, and you can actually show this. What about linearity? Yes, it is. What about time invariant? No, it's not time invariant. What about memoryless? The rates are different, right? My rates are slower, right? So I need to collect stuff in order to be able to output it, right? I get a lot of stuff and I output a little bit every time. Okay. What about stability? Yes. Okay. So here's an example why compressor is not time invariant. Okay. Let's say we have this signal over here and we have m equal 2. We'll get this signal, right? We only get every second signal. Okay, every second. What if we shift by one sample? What would happen? That's not shifted, right? I get zeros. Okay? So if I shift the input, I'm going to get a different output. Okay? So that could be an issue. What about another nonlinear system? Here's a really cool one that I really like. One of my favorite. A median filter. A median filter takes a window of samples and then computes a median operation. So sorts them and take the one in the middle. Is that linear? Absolutely not, because I said example in nonlinear system. Right? And you can show that it's nonlinear, and I'm not going to actually go over it. You can actually look at the example. It's pretty, it's pretty easy. You can have x1 and x2, and this is the result of x1 plus x2. You run it through a median filter, you get y1, you get y2, and if you add them, you get this, which is not this. Okay? It's very simple. Okay? So it's a nonlinear system. Very simple nonlinear system, extremely effective. Let me give you an example. Anybody ever listen to This American Life? Like it's a podcast? Raise your hand if you do. Oh my God. This is like, this is from a radio point of view, this is like something else. The level of journalism that comes out of this program is just unbelievable. I really recommend it. Listen to this. It's unbelievable type of journalism that people put out for free by a public radio station. Unbelievable. Okay, so I really recommend. There's one particular episode there, which is called "The Greatest Phone Message of All Times." Okay, it's pretty funny, I have to say. But it's about a story about some college where they had this phone messaging system, and the message started to.
There comes a time in life when we hear the greatest phone message of all time, and when we hear this, you dare to believe it.
Okay, so the whole, it's just like a 15-minute story about this message, and somebody goes back, 15 years later, tries to track that message and like what the story behind it. But anyway, you should listen to this episode 2 or 3. But anyway, let's say come the message, but instead of actually getting the message, you have something that's corrupted. You can hear it. So here's the thing. If you look at speech signal has about 2.5, like especially on phones, 2.5 kilohertz wide, right? When you look at the spectrum for this corrupted speech, you see like lots of kind of energy all spread out. And there's more energy here in the speech, but it's corrupted. Anybody has an idea how to try to clean it up? Low-pass filter, right? That's the thing. Is low-pass linear? It is linear, actually. Okay, so you try to do a low-pass filtering, and you get this spectrum, right? It kind of looks cool, right? So let's listen to this. It's a little bit improved, right? There's less noise, but it's not great. So if you look at the time signal, there's something very special that happens here. This particular corruption is what's called kind of wideband noise. It's noise that is because of like spike noise. Okay, so you can get that from like a faulty connection and things that drive things to the maximum. Okay, terrible. The thing is, when you do low pass filtering, This thing over here, when you low-pass filter, it's kind of like averages it out and like gets this corrupted, you know? This thing pushes it up, pushes it down. Like, it doesn't work. These are outliers that really screw you up. So, anybody has an idea of filtering this, what's called shot noise? Well, what a median filter would do, right? Median filter is really robust to outliers, because outliers will always be on the sides, right? They'll never be in the middle, because that's the definition of an outlier, right? So if we go and do a median filter, this is what we get. Yeah, we do hurt a little bit our signal, but do we hurt it so much? I don't think so. And here's the message. After applying for that particular signal that was corrupted, a median filter. Here's how it sounds. But it completely cleaned it. Completely. You can barely hear any noise. So this is what's amazing about nonlinear processing. You can get significant gains by introducing nonlinearity. And some people can make their whole career out of nonlinear processing. Some people. But you can get significant gains over linear systems. They're way more complicated sometimes to analyze, but could be much gain. We're going to continue next time. Sorry for stealing 2.5 minutes, but I'll pay you back next time when I'm going to be late. All right.